This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. I got with me my co-host, Chuck Nice. Chuck,
Hey, Neil, what's happening?
today I think is one of the hottest topics in all of science. We want to figure out what dark energy is, who made it, where's it coming from, where's it going, and will we all die? Will we all die?
Once we find out what it is. Yeah. The universe can't tell us unless it kills
Unless
us.
it kills us.
Yeah.
Unless it kills us.
Right.
We've got with us for this episode my friend and colleague, Jason Rhodes. Jason, welcome to StarTalk.
Thank you for inviting me. I'm really looking forward to talking about dark energy with all of you today.
Yeah. So
Yes.
you hail from the Jet Propulsion Labs. We all know that's in Pasadena, California.
JPL.
It's a branch, one of 10 branches of NASA, and JPL is affiliated with Caltech. And so that makes sure you all are doing the right things. All right, y'all, no slouching.
That's right. we have two bosses here,
Yeah.
Caltech and JPL. Caltech and
Uh,
NASA.
and NASA
Yeah.
and NASA. So and JPL, right?
That's right.
You've got NASA headquarters, JPL headquarters,
Wow.
and okay. So no
God.
slouching there. So your research interest, what I like about you for this conversation is you not only have deep interest in dark energy, which we'll get to in a minute, which we all do, but you're not just talking about it. You're actually trying to solve the problem using experiments, using telescopes, detectors, balloons. And I want to get into how all that works. How could a balloon launched from Earth tell you anything about dark energy in the universe? So,
Unless it's a Chinese spy balloon.
oh, those!
You know. Hey, those balloons are able to tell you a great deal.
All right. So first, just remind us all what dark energy is and how you got into it.
Well, dark energy is really the name we give to our ignorance of what's causing the universe to expand faster and faster over time. And about 25 years ago, two groups of scientists were trying to understand how fast the universe was expanding and how that expansion was slowing down due to gravity. And so they were doing these experiments, and they almost simultaneously came up with the same result, which was very surprising. It was not slowing down due to gravity, but instead that expansion was speeding up as if something was pushing the universe apart. And they gave the name of whatever that is, dark energy. And we are still 25 years later trying to figure out what that dark energy is, where it comes from, and what it's going to do to the universe in the future. And right now we think dark energy is the dominant component of the universe, and it is only going to become more dominant over time in the future.
So this is an invasion, what you're saying. We're actually being taken over. We're being taken over by this force.
We really are. And if you look back deep into the universe's history, 10 billion years ago, dark energy was a very subdominant small component of the universe. Now it's the dominant component of the universe. And as I said, 10 billion years or more from now, it's going to be even more dominant, where the universe is completely dominated by this dark energy. So it really is an invasion.
Well, so how do you get if the universe is expanding and getting thinner, how do you get more of something?
That is a really interesting question for us to ask. So one of the theories of dark energy is maybe it's a property of space-time itself. And that is, when there's more space-time, there's more dark energy. And as there's more dark energy, it's causing space-time to expand faster and faster, making more and more dark energy in this sort of runaway effect. And for some...
So it's self-propagating? Is that the
a
deal?
little bit like that. And for some physicists, they don't like this because it really sounds like a violation of the conservation of energy. We're getting more dark energy over time. So if we think of dark energy as energy in the classical Newtonian physics sense, we're really not conserving energy in the universe, which is a very distasteful concept to some physicists. On the other hand, the equations we're using to describe dark energy are just equations that have been around for 100 years, come from Einstein, and they seem to fit the universe. So the universe is telling us something very profound here.
It's telling us something profound, but it's also contradicting something profound at the same time. It's very much like being in a weird relationship, where you don't know what to do. Yeah,
I would say you're allowed to contradict something profound with something equally as profound, and then, put it in the octagon and let it sort itself out.
nice. I like that.
So
Two postulates enter, one postulate leaves.
so if the universe is expanding, then the gravity is thinning, so the dark energy is becoming ever more powerful regardless, and relative to gravity, it's getting that much more powerful. So gravity doesn't stand a chance going forward.
That's right.
Man.
We are seeing a universe that's increasingly dominated by this dark energy.
So Jason, that the original results from 25 years ago, which if I remember correctly, got the Nobel Prize, the discovery of dark energy, they use like supernova exploding like out to the edges of the universe, and you can get a distance from that. You get a distance from some Hubble laws, and so are there other ways to verify that, to know that what we're thinking is really that these other measurements are really true?
So, the original supernova experiments that they did in the 1990s to discover the dark energy were looking at supernova out to a Z or redshift of about 1. And one of the things we'd like to do is we'd like to push that push those measurements back further to a redshift of about 2. And for that, we're going to use the Nancy Grace Roman Space Telescope, which NASA will launch in 2027.
Whoa!
Wait,
What?
you mean the crime lady from HLN actually was an astronomer as well?
No, in fact,
Who?
Nancy Grace Roman was NASA's first chief astronomer soon after NASA was formed in
Oh,
1958. And she was a champion of space telescopes. And in fact, she was called the mother of the Large Space Telescope. And the Large Space Telescope, when it was launched, had a different name, and that was the Hubble Space Telescope. So she was really one of the
oh,
Mm.
chief people pushing to build the Hubble Space Telescope, which of course has transformed
wow.
our views of the universe and astrophysics in so many ways.
Look at that. Behind the scenes, a great woman. And of course, out front, some dude taking all the credit.
What are you
Uh,
talking about?
Mr. Hubble. I mean, don't get me wrong. I understand Hubble was an incredible scientist and he deserved to have his name on the telescope. But who knew that behind that whole project, there was a woman pushing the entire thing? That's amazing.
So, Jason, I know that Lyman Spitzer wrote a very early research paper after the Second World War, realizing that if V2 rockets can leave the atmosphere and do harm, they can also launch something into orbit, like a telescope. And he knew the value of telescopes above Earth's atmosphere for this purpose. But he wasn't active with NASA, right? And that's somebody at NASA inside has to make this happen as a goal.
Yeah, sure. And Lyman Spitzer was a huge voice in the science community, making space telescopes happen at the same time that people like Nancy Grace Roman at NASA were making them happen. And of course, Lyman Spitzer had a fantastic infrared space telescope named after him. And so in 2027, Nancy Grace Roman is finally going to get her due with the space telescope named after her.
There you go.
Look at that.
Okay.
The women, first in, last out. Look at that. God, so predictable.
So, what are these telescopes going to do? Are they still going to look at supernova, but just farther away?
So one of the things Roman will do is look at supernova, but Roman is going to join a telescope already in space called the Euclid Space Telescope and use a couple of other techniques to look for dark energy. And those techniques include weak gravitational lensing, where we look at small distortions in the measured shapes of background galaxies to measure the dark matter between us and those galaxies, and also a technique called baryon acoustic oscillations, which is a way of talking about the clustering of galaxies, how close galaxies are to each other.
Wait, so you're talking about dark matter there, right? Not dark energy.
That's
Is that
right.
right? Did I hear you right?
You did. And so one of the things that we know is that dark matter, which is another mysterious component of the universe, interacts with gravity. So over time, dark matter becomes more clustered due to gravity. Gravity tends to pull things together. But at the same time, the dark matter is pushed apart by the dark energy. So by looking at how dark matter clusters and changes over time, we're learning about not just the dark matter itself, but the interplay between gravity and dark energy. And so that's how we learn about
Oh.
dark energy, by studying dark matter.
Okay, so you know what to expect from dark matter, and if it doesn't live up to those expectations, something else is meddling within it, and you can track that over time.
That's right.
Okay, that's interesting. All
Wow.
right. All right. Now, what's this about balloons?
Well, the reason we want to go to space with a telescope is we want to get above the Earth's atmosphere. The Earth's atmosphere causes things to twinkle, causes stars to twinkle. I have a 2-year-old daughter, and she started to sing "Twinkle, Twinkle, Little Star," and I want to stop her and say, "No, no, it's not the star that's twinkling. That's actually the atmosphere." I hold myself back, but we want to get
Fun
above
dad,
that.
Yeah.
fun dad you are.
Yeah, yeah, yeah. Sweetie, you should be singing "Twinkle Twinkle Refracting Atmosphere." Okay.
That's right. I'll correct her when she's 3. But
Worst dad ever, right?
the atmosphere also absorbs a lot of wavelengths of light, so we want to get above the atmosphere. But a rocket launch is expensive, and it takes a lot of time to develop a space mission that's going to go into space, and you can't tweak it.
Right.
So one of the things that NASA and other space agencies do is they put telescopes hanging from balloons, and these are huge balloons the size of a football stadium, that are filled with
Wow.
helium, and they take these telescopes to the edge of the atmosphere so that they're above most of the atmosphere. And then we can do days or even weeks of observations above most of the atmosphere. And so we just did that earlier this spring with a balloon called Superbit, which circumnavigated the Earth about 5 times from a launch in New Zealand. It's just the winds that take it around the Earth. And all that
Right,
time, we were
right.
making observations of clusters of galaxies, trying to understand the dark matter in those galaxy clusters.
China didn't shoot it down.
No, in fact, NASA brought it down on purpose over land, because most of the Earth is ocean, and we wanted to recover the telescope and the hard drives. So NASA eventually said, all right, we're going to bring it down
course.
where we can send a team to get the hard drives, because if they fall into the ocean, we're not getting those back.
Well, I mean, listen, why not? You're setting up a balloon. You want to tell me you can't attach a little raft to it, or some swimmies, so that you can so it will float and you
Yes, yes.
can get the hard drives. I mean, even if something were to happen by accident, and listen, by no means am I denigrating the great efforts that you guys do, but I'm just saying, as a person who's been to a pool, that if you put some swimmies on your telescope, you might be able to recover it in case of emergency.
A minimum
That's
a
all.
pool noodle, you know.
Exactly.
What?
Pool noodle.
That would have been a good idea, yeah. But we did come up with what I thought was a crazy idea about 10 years ago. We said, hard drives are cheap compared to everything else. Let's eject some hard drives from this balloon and bring them down on a glider or a parachute during the mission. And so we had a crazy idea, and we pursued it a bit. And in fact, we actually employed that on this Superbit mission, and we dropped some hard drives from way up in the atmosphere, and then had them fall to the Earth, and then we can go recover it. It turns out we didn't need to do that because we used satellite downlink of the data, and we were getting it all down, but we didn't know how well that was going to work. So we had this backup of just dropping the hard drives out of the sky and finding them where they fell to the ground.
That makes sense. In this age of 5G, you can just almost in real time, take the information as you're collecting
yeah,
it. So yeah.
Back in my day, back in my day, we we would speak of bandwidth. We would compare bandwidth to the bandwidth of FedEx. Right? You just take a tape, hand it to FedEx, and they deliver it across the country faster than the uplink would allow you to transmit the data. So
I remember when we used to put satellites in space using a giant rubber band. It was like a slingshot. It was made by Acme.
I'd like these other methods to try to think about dark energy. So all you're doing, though, is making more measurements of what we know is there, but you're not really telling us what it's made of.
Well, the way I like to describe it is there's lots of theories for what dark energy might be: a new force, a property of space-time, uh, some mysterious particle, lots of different theories. And the theorists have really had a field day. And these theories all produce results or would produce results in the real world that are slightly different, and especially different with these different measurements: supernova, the baryon oscillations, and the weak lensing. And so what we're trying to do is gather all the data to rule out huge classes of theories and say it wasn't that, it wasn't that. And it's sort of a last man standing thing where we say, okay, it's this one.
There might be just one left that you can't rule out, and so maybe that's it. I get you. Okay.
Mhm.
All right, cool.
Hmm.
All right,
Interesting.
Chuck, let's go to Q&A here. We got
You
some
want to go to Q&A?
let's got some Patreon members here
Here
who
we go.
support us at the level of $5 a month. That's all. Less than a cup of
That's all.
Starbucks coffee. You get to ask questions.
And thank you all for supporting us on Patreon. And this is Calvin Waite. And Calvin says, hello, Jason, Lord Nice, and the long-time reigning king of StarTalk and the cosmos, Neil deGrasse
They
Tyson.
do that because they think that's going to get their questions answered more. But apparently
And
it
they're
is.
right, because I'm reading it. Clearly,
No.
sucking up works.
All right.
No, this is why I'm reading it, because he says, I am 13 years old and I recently became a Patreon member. This is a 13-year-old kid who is taking his paper route money and giving it to StarTalk so that he can ask questions. So the rest of you have no excuse at all. Okay.
Well, he doesn't know what the term paper route even means. So
no,
fine.
he doesn't.
Right. Okay.
I know. Right. I'm dating myself because I had a paper route. I am currently on a trip in Talkeetna, Alaska, and I send you my regards with this question. Due to the theory that the space and time places flip in a black hole.
Wait. That's
hole,
Talkeetna. Talkeetna.
Talkeetna.
Yeah.
Is that how you say that?
Does it spell that way?
It's just exactly
Yeah.
that
My
way.
wife is from Alaska, and that's a.
I said Talkeetna,
Yeah,
but it's Talkeetna.
Yeah. Mm-hmm.
Okay, Talkeetna. Due to the theory that space and time flip places in a black hole, if said black hole is comprised of dark matter, could we harness this dark matter or energy to travel through time and create wormholes to distant galaxies? I've been a fan for a very long time, and I'm so excited to hear the answer.
Oh. Yeah, Jason. What do you got for that?
Well, I'm going to say, unfortunately, Calvin, I think I had the name right. Unfortunately, once matter, whether it's dark matter or normal matter, falls into a black hole, it's really gone to us, and we have no way to access it. And so a black hole could have normal matter in it. It could have dark matter in it, but that matter is gone, and we don't have a way to access or harness the matter inside the black hole.
Do you think the black hole cared whether it ate matter or dark matter? It just ate.
I think it was indifferent. It's going to grow either way.
It doesn't discriminate.
It doesn't care.
Now, what's going to be fun is if Calvin actually invents this device in his basement and then comes back and says, see, I was right all along. See, that's what's going to happen here.
You know that sort of reminds me, Neil, that a lot of people think scientists never want to be wrong, but I would be thrilled if Calvin invented that. And in general, scientists are thrilled when their experiment shows something that makes them go, huh, that's not what I was expecting. And so that's what happened with dark energy 25 years ago. We as a community said, that is not what we were expecting. And it's really exciting to be alive in a time where we find something completely unexpected.
This was Isaac Asimov's edict. He said the clarion call of the scientist is not Eureka. It's that's funny. You see some result. He said, I don't know what this is. That's the discovery. It's not Eureka.
Yeah.
It can be Eureka, but mostly it's not. Right.
Yeah.
Right. All right, Chuck, give me more.
All right, this is Roland P. And Roland P. says, hello, Dr. Tyson, Lord Nice, and Dr. Rhodes. My name is Roland, and I'm writing from Cologne, Germany. Sorry, Chuck, my last name is unpronounceable to you. You don't even give me a chance to butcher your name, man. You don't even give me a chance to
He just
butcher it.
abbreviated with a
So
P, right? That's
he just went with the P. You know what I mean? My question is about the Euclid mission.
Mm.
When they say the probe will generate a 3D map of the universe, how do you cope with the fact that most of this map is outdated? The stars you are seeing might not be there anymore. The galaxies have moved, they've merged, etc. During the billions of years the light took to reach us, what you're looking at is a ghostly image.
Ooh.
Oh, look at
Ooh.
that gauntlet thrown down there,
Ooh.
Jason. What's going
That
on?
is a very interesting question. And the answer is we don't want to know necessarily what those parts of the universe look like today because we assume that they look very similar to the parts of the universe close to us that we can already see. We want to see what the parts of the universe looked like in the past. And that's why we're looking further and further out. We're using infrared light to look closer to the beginning of the universe because we want to see how the universe has evolved. So we don't want a static picture of the universe today. We want to measure this three-dimensional map where looking further away in that third dimension is also looking further back in time. So we want to look at the time evolution of the universe because that's what's driven by this interplay between dark energy and gravity. So that what Roland has brought up is not so much a problem with Euclid. It's what Euclid is designed to measure.
Euclid is a European Space Agency, correct?
Yes, Euclid is a European Space Agency mission that launched July 1st, 2023. I'm wearing my Euclid shirt because I'm the U.S. science lead for Euclid. NASA provided some great infrared detector technology to Euclid, and we have over 100 NASA-funded U.S. scientists working on Euclid with our European counterparts.
So when these agencies come together and collaborate, but yet you're still working independently, is there any competition or jealousy when somebody comes up with something great and the other part did not? Tell the truth, please.
Scientists are still human, so we can be jealous when somebody else has a good idea or a great mission from another agency or another country. But what we're seeing increasingly is scientists from different countries and agencies from different countries working together because the telescopes and the projects are becoming more complex and more interconnected. And so we have a telescope like Euclid that will work in certain ways, and it's going to be very complementary to NASA's Roman telescope, which the European Space Agency is participating in, just like NASA participated in Euclid. So we're working together to build all of these telescopes on the ground in space, and we're going to use the data from all of these telescopes as a science community together to get the best constraints on dark matter and dark energy and the properties of the universe.
So I like the idea that you're saying we're looking back in time on purpose, and the fact that galaxies might have collided or stars won't be there by today. You don't care. You care that they were there back when we saw them. So that's an important distinction to make here. There it is.
Interesting.
All right, Chuck.
It's very cool. Very cool. Let's go to Fabiola Horvath. And Fabiola says, "My dear Dr. Tyson, Dr. Rhodes, and sweet Lord Nice, Fabiola here from Hungary. We are international for sure today, man. In my opinion, Euclid might be one of the most exciting research tools ever built. Can't wait for the results. I wonder if it will be able to shed light on what the Great Attractor might be, or debunk its existence once and for all. Thank you. Always, I will always keep looking up, and please tell me your thoughts on the Great Attractor."
Mm.
So the Great Attractor is a group of galaxies and the associated dark matter associated with those galaxies that's relatively nearby in the universe and is attracting other galaxies towards it through its gravity. And so Euclid will be able to produce not just a map of the dark matter there, but a map of the dark matter over fully a third of the sky. So 1/3 of the sky, and that's the best third of the sky in the sense that it's the darkest and furthest away from our Milky Way, which is littered with stars which block our view of the distant galaxies. So Euclid will produce a huge dark matter map that not only can tell us about this great attractor, but many other, thousands of other dark matter conglomerations or galaxy clusters out there in the universe, much further away than just the local universe that we've been studying for the last 100 years.
But what's been doing the attracting in the Great Attractor? Is it related to the work you're doing?
Well, we think it's galaxies and the dark matter associated with those galaxies. So it's just a big conglomeration of mass.
As they coalesce and all this mass comes together, it just creates more of an attraction. Is that the deal? Or is it something like the Great Garbage Patch where there's a natural flow to a particular point, something like or something even more like the pooling of a Lagrange point? Do you guys, or do you know? I'm just at this point, I'm just throwing out a bunch of stuff.
Well, in, in fact, this is very related to one of the ways that Euclid and in a few years Roman will probe dark energy. We're gonna use a technique called redshift space distortions, and what that is it's us looking at galaxies in redshift. So we're gonna see where they are in three-dimensional space. That redshift tells us the distance, but there's some distortions there in those measurements because there's a local movement of the galaxies as they're attracted to big conglomerations of dark matter. And so we're looking at those sort of very minute local distortions in how the galaxies are moving. And encoded in the motions of the galaxies is a lot of information about the dark matter. And as we've talked about, that information about the dark matter is going to tell us about the properties of dark energy in the universe.
So the movement of the galaxies, separate from the expansion of the universe, is they are your probes for the structure of where all the gravity is local to that region. Is that a fair way to characterize that?
That's exactly right. Yes. We want to
Okay. All right.
probe
Cool.
that local structure.
Yeah. Yeah. All right. All right, Chuck, keep it going. Time for a few more.
Okay, so this is Ed Ianowski who says, "Greetings from Portland, Oregon. In considering things like dark matter and dark energy, it seems we don't use Occam's razor that much. Why do we assume that dark matter is matter at all, or that dark energy is indeed energy? What about the nature of space itself? We know space can warp, stretch, expand. Just because regular matter warps space, do we have to assume that the warping associated with this dark matter is also caused by some sort of matter that we call dark? Couldn't it just be a part of the nature of space itself? What is space? And why does it produce a vacuum energy, virtual particles, and the such?" Okay. All right.
That's a lot.
Okay.
Well,
Wow.
That was a lot, wasn't it?
Wow.
I'm gonna
That
I'm
was
gonna
a lot,
address the
man.
dark matter part first. So, dark matter
Okay.
was first theorized, close to 100 years ago, and the first real strong evidence for dark matter was found, say, in the 1970s, and before that by a pioneering astronomer named Vera Rubin, who looked at the rotations of galaxies and said these galaxies are rotating faster than they should be um, if the galaxies are made up of just stars and dust. So there must be something else in there. And so this was the first real evidence for dark matter. And at the time, dark matter was just the name given to whatever was causing this rotating galaxies to be rotating faster than we thought they should be. However, over the course of the last half century, we've had an increasing number of different observations across all areas of astrophysics, which have told us that this dark matter is there. It's some sort of particle, and it is a mass, just like normal matter, but it just only interacts gravitationally. And so the dark matter has gone from being sort of the way we explain some observations to being something predictive. That is, I am able to now say, okay, I think this is the properties of dark matter, so I should go out and I should measure something. And indeed, I confirm that, yes, there probably is this dark matter out there.
Wait. You don't have a dark matter particle yet, though.
We
Right?
do
So
not.
what are you saying?
Well, so there's two ways to look for dark matter. There's the astrophysical way.
Why'd you say that up front?
Okay.
You said, well, we don't have any kind of dark matter particle, but we still want to think it's matter. That's what you just said.
Yeah. Okay.
Okay, so what gives you the confidence that dark matter is made of matter if we don't have a dark matter particle yet?
So we see a lot of clustering of dark matter at different levels in the universe. So there's what we call a hierarchical clustering of dark matter that we can measure. And if it's a particle, that's the exact type of clustering we would see. So, and we see
You'd
this
expect. Okay,
astrophysically. So lots of groups on the
got it.
ground are trying to detect
Hey,
the dark matter
look at that.
particle, and they so far have only come up with what we call null detections.
Okay,
Wow.
all right.
That is so cool.
Okay, so
Yeah.
null
Yeah,
detections is they think it's a particular kind of particle. They set up an experiment and they should see that it's not. Then they think, is it a different kind of other particle? You set up a way to detect it and it's not. So these are all the null detections. So once again, maybe some other particle will be the last man standing.
That's
Right.
right. That's right.
Right. Right. Okay.
So you guys, I mean, that's a long process. You just have to keep ruling things
Yeah.
out. Like you're
That's half
you're
of science.
striking the list.
Half of
Yeah.
science is ruling stuff out. Half.
It's just
Yeah.
ruling it
Yeah, that's
out.
a lot of
Okay.
science.
Wow.
What?
Okay.
And okay, now what about the guy kept going though? He didn't stop there. Where else did he go?
No,
Well,
he
he
didn't.
asked
With the
about
question.
dark
Well,
energy, and indeed, dark energy may be simply a process or
A property of
a property
space
of
time.
space-time. That's right, a
Mhm.
property of space-time.
right.
And I don't know that dark energy was the best name for our ignorance of what's causing the accelerating expansion of the universe, but I wasn't the one that was asked to name it. Uh, so that's the name somebody came up with. I think it was actually a U.S. astrophysicist named Mike Turner who came up with the name dark energy, and that's the name that stuck. But it's not an energy in the classical physics sense of an energy that we think about. It's perhaps some property of the universe. So we don't really know. And that's where we really are just designing these experiments to rule out big classes of theories.
I would add that the dark matter could be literally and accurately named dark gravity, but no one picked up on that, and so because that's what it is, right? It's gravity, and we don't know where it came from, so it's dark gravity, and people just assuming that matter you need matter to have gravity, and I thought that was overstepping, given our state of ignorance at the time. Yeah.
That's
Interesting.
very possible. And I think even dark matter isn't the best name because you can see the screen behind me is mostly dark because it's absorbing the light. Well, dark matter doesn't absorb or give off light. So it could be more accurately now called clear matter because the light passes right through it, but it's the path of the light is distorted by the gravity, but the light passes right through it.
So that it doesn't interact with the light at all?
No, it doesn't interact with the light at all. It only bends space-time. The dark matter bends space-time, so the path of the light is curved.
I got you. But see, that happens anyway
Right. You
for
get
what
that
I
for
call
free.
light surfing.
Yeah, you get that
You
for
get
free.
that for free.
Yeah. So,
Right.
but Chuck, your hair is dark because it's absorbing light, hitting it, and not reflecting it back to me. It's interacting with the light.
Yes. Thank you for noticing. I appreciate that.
Give me a couple more. Bring them on.
All right,
Jack.
let's go with Kevin Curry. And Kevin says, "Hello, this is Kevin Curry from Sparks, Nevada. My question is about gravity. I understand that gravity moves in waves and propagates at the speed of light. However, do masses with high gravitational fields affect the waves from other masses? If so, is it possible to tell them apart? If not, how can we know the gravity from one mass actually came from the specific mass and was not modified by another mass between us and the original masses? In short, is gravity affected by gravity?"
Ooh.
Ooh.
I like this question because it allows me to mention a new way of measuring the universe that's become increasingly popular and increasingly possible over the last decade, and that's by measuring gravitational waves. These are ripples in
Right.
space time caused by massive particles, or not particles, but massive objects like black holes orbiting each other, or neutron stars orbiting each other, and they give off these gravitational waves. And we can see those gravitational waves interact with each other, and they interact with our very sensitive detectors here on Earth that are looking for very, very minute changes in the path of a wavelength of laser light that are caused by these ripples in space-time. And that's only in the last decade, or even less than a decade, that we've been able to measure these. And it's an entirely new window on the universe. Previously, we had used light, whether that's light that we can see, or radio waves, or X-rays, but always electromagnetic radiation. And now we're building telescopes and using different techniques to study these gravitational waves, which are telling us about some of the same phenomena, but in a very different way. So it's a really exciting time to be an astrophysicist.
Well, if two of them intersect, do they resonate in some way? Do they cancel each other out? Two gravitational waves moving through space, what, from two different
I
origins?
think they can. They can interact. If you imagine ripples on a pond, if you throw a pebble in and you throw another pebble in, you can get the interaction. And I think it's very similar for gravitational waves. You can get that interaction, and that's likely something that we'll be able to measure in the future as we get ever more accurate detectors. And in fact, there's a mission that the European Space Agency is going to build in hopefully the 2030s. And NASA will participate, called LISA, where they're going to put these lasers in space to measure gravitational waves in space.
Mm. Over a much bigger baseline than just two locations on Earth's surface,
That's right.
right?
Yeah.
So you can get to see that. Okay. All right, I'm loving it. All right, Chuck, deep
Yeah, these
questions.
people are on point today, I
And by
have
the way,
to
a
say.
13-year-old has already created the wormhole. I just got the report.
Yes, exactly.
Congratulations.
This is Thomas Cochran, who says, "Greetings from Kansas City, Missouri. I'm curious how Euclid will go about exploring the mystery of dark energy with instruments that are tuned to collect data in the visible and near infrared spectrum. Any speculation on how we can circumnavigate the issue of collecting data on something that doesn't interact with our universe in this typical way? Thank you for making us all smarter."
Mm.
Right. So we just learned that it doesn't interact with light. So he's asking, if it doesn't interact with light, how are you using light to actually measure
So
something?
we're measuring the properties of galaxies, and those properties are the shapes, the distances, and the motions of the galaxies. And encoded in the shapes, distances, and motions of galaxies is a lot of information about dark matter and dark energy. We can't measure dark matter and dark energy directly, but we measure those properties of the galaxies using visible and infrared light. And then we use the techniques that I talked about earlier, the gravitational lensing, the baryon acoustic oscillations, the redshift space distortions, uh, by measuring those galaxies to discern the properties of dark matter and dark energy.
Everything's a bank shot. Everything you're doing is a bank shot. That's basically what you're saying. It's like, yeah, we don't try to sink the basket. We go off the backboard,
All right.
and that's the
But
deal.
whatever way you
Okay.
can, right? I mean,
That's right.
yeah, yeah. I'll tell you just an aside to this, Chuck. You know the electron, which we all talk about, and you know what the charge is, and we don't know how big it is.
Oh, wow.
We've never measured the size of an electron ever. As far as we know, it's infinitesimally small. So, what does it even mean to talk about an electron as though it's an actual particle? When in fact, what we really mean is whatever it has these properties that we've measured for it. And it's the properties that interact with everything else we care about.
So if we don't know how big it is, so there's been no actual sighting of an electron.
Basically, but you can cite the effects of an electron, but not
Right,
the electron
yes, and
itself.
he's yeah.
Right, right. So
One
that's all
yeah,
Jason is saying. I think, Jason, is that
right.
the more precisely you know the galaxies, the better you are able to know what effect the dark matter, dark energy has on the galaxy, because that's otherwise you're not catching it in the open field, right?
That's right, with one subtlety, in that these effects of dark matter and dark energy are very subtle, And so we want to measure not just a very precise measurement of a galaxy. What we're going to do with Euclid is we're going to measure shapes of over 1 billion galaxies and to do a statistical study. And so
Mm-hmm.
it's really these new telescopes, Euclid and then Roman in a few years, are going to provide huge amounts of data, huge amounts of measurements on galaxies that allow us to discern the properties of dark matter and dark energy through statistical studies. So our measurement of any one galaxy,
If 1 billion galaxies, you got AI helping you in there somewhere,
we
right?
we
There's some,
we have to have AI helping
yeah.
us
Right.
because we don't have enough grad students to look at each galaxy individually
Right. Yeah.
over
Exactly.
time. Yes.
Yeah.
You need something that can look at millions of them all at once and say, that's not necessary, or we don't have to look at that, or those
Yeah.
are all the
Yeah.
same,
Yeah.
or
Yeah.
here are the anomalies. That makes sense.
Mhm.
That's super cool, man. Damn.
All right, Chuck, we got
God,
time for
you guys have such a cool job. It's amazing.
Well, we got time for one last question, I think, Chuck.
This is Gavin Bamber. Bamber says, hello from North Vancouver, where it doesn't matter that I have energy.
What? Okay.
Okay. Yeah, I think that was a joke. He says, why is it called the Euclid Mission? And how does any of this pertain to geometry? Okay, so he's
Oh,
going very literal
he's
with the
calling it out.
Euclidean calling. Yes.
Right.
Calling it out.
So when we were looking for a name for this mission, we thought about what are we measuring? And when you measure the expansion history of the universe, one way that scientists describe that, they say you're measuring the geometry of the universe, what the universe looks like, and who is more associated with geometry than the father of geometry, Euclid, who wrote a textbook on geometry, you know, 2,000 years ago, that was still in use up to a couple hundred years ago. So this was an amazing scientist who really founded the field of geometry. And so we are trying to measure the geometry of the whole universe. So it seemed an apt person to name this mission after.
Now, I would add,
Okay.
however, just to be snarky, but I agree with everything you said, of course. But to be snarky, when Einstein showed that matter and energy distort the fabric of space and time, Euclidean geometry was no longer Euclidean. It was non-Euclidean geometry. So everything that is in the universe is a negation of the flat plane, flat space world that Euclid had described. But he did start it all, so I give him that.
Yeah. Okay.
No, because Chuck, you remember parallel lines never meet. Okay,
Right.
in Euclidean
Exact- well,
geometry,
and we know they. Yeah.
in non-Euclidean geometry, they either meet or diverge. Okay, they don't
Right.
just stay the same distance.
They don't
Weird
stay-
stuff
stay-
happens.
Right.
There was a whole other step that everybody had to take, and it was quite an adjustment, I might add, to go there. But non-Euclidean geometry. So we should have called it the non-Euclidean mission.
The non-Euclidean mission. Wow, that
That get people looking that stuff up at that point.
man, that's a serious diss right there. It's the non. By the way, Euclid, this is not your mission. Okay, just letting you know, this is the non-Euclidean mission. Okay.
So, Jason, this is great. It looks like you're going to have new knowledge to surface in the coming months and definitely years. So, give us a call when you got something to report, and we would be delighted to get you back on.
Would love
find
to.
out, because
Yeah.
for me, it's the biggest mystery in all of science now is the dark energy
Yes.
problem.
It really is very perplexing.
And so, Jason, also thank your three bosses, the head of JPL, the head of Caltech, and the head of NASA for lending you to us.
Yeah.
You'll do that
Yes.
for
I
us.
will. Thank you. Yeah.
All right. Excellent. Thanks for being on with us. Chuck, always good to have you, man.
So much fun. Always a pleasure.
All right. This has been StarTalk, our dark energy edition, with a touch of cosmic queries within, and my friend and colleague, Jason Rhodes from JPL. This has been StarTalk. As always, I bid you to keep looking up.